Good afternoon, student. This is Mr. Teo again. Today we are going to have Lab 6. We're going to discuss about Lab 6. Without further ado, let me turn on the video. The PowerPoint for the Lab 6. Now, for Lab 6, we are dealing with the process modeling through system identification, right? So again, in your Blackboard, you should be able to see the lab sheet, which is system identification. So you follow the detailed step based on this. And you have the slides, which is this particular slide that I'm sharing with you right now. And of course, for this lab, I don't need you to connect the VI. The whole VI is given to you. It's called Motor Modeling 2014.vi. So please use this VI to run the actual lab. Then also for this particular lab, if you are running it at home, running a lab view at home, you basically need a control and design simulation add-on, right? And of course, there's also alert feedback for this week. So if you got time, please try to do it. Now, just to relate this particular lab back to your theory, which is block diagram manipulation on week 8. Now, the purpose, of course, really is to get to simplify single blocks transfer function, right? So basically, what I'm trying to say here is you may have in a plan whereby the case is you have a lot of sub-blocks, right? So based on the application of block diagram manipulation, if you apply rule 1 and rule 8 at each of the individual sub-loop, you may be able to simplify into one single block. This is what we mean by block diagram manipulation. Now, after you simplify this block, then you are able to analyze the block using the simplified block version. Now, each of these blocks, G1, G2, and H1, etc., how do we get it? So first of all, in order to get all these G1, G2, G3, we basically have two approaches. One of them is a physical approach, basically looking at the first fundamental first principle parametric way and relate it to various variable of interest. That's one way. Now, the second way, we basically do the modeling approach, that is collecting data and match with the preset model. So only when it can be put down as a transfer function mathematically, then we can process it and manipulate it further, right? So a lot of times, if you cannot put it in a mathematical formula, then controlling it or manipulating it is a lot more difficult, right? So again, for Lab 6, the learning objective is basically using a pre-selected model and output measurement using LabVIEW for the unit step response. Unit step response means that I generate basically a step response here, right? And then I find the model for potentiometer and tachometer. So this is a motor module that potentially has one potentiometer output and one tachometer output. So we are trying to check if I excite the motor module at the input by a step function, what do I have at the output of potentiometer and tachometer? And basically we are using the pre-selected way of modeling, meaning that maybe model A or model B, right? So for the motor module, it looks something like that. That contains basically, of course, your analog excitation, the step function you will pump into the analog input. And then, of course, either if you are performing a potentiometer measurement, then you will take the potentiometer output. Now, if you are doing the tachometer measurement, then you will be taking the tachometer output. Now, please note the setting here at the bottom right-hand corner. This switch is supposed to switch to V in, and this switch is supposed to switch to V out, right, for the motor module. Now, the overall connection between the motor module power supply and LVs are basically looks this way, right? Basically looks this way. So in a nutshell, the power supply is basically connecting the plus minus supply voltage to this area here. And then there's also a 0 to 5 volt that is connecting to the logic inside. And then, of course, the LVs will be generating a signal, analog signal in, and picking up an analog signal out from either the potentiometer or tachometer output. And likewise, your LVs will also be linked to your PC via the USB. right? So this is a zoom in version of how you connect your Moto module, how you connect your LVs to your, basically your, how you connect your LVs to your Moto module, right? So that's all the pin with a jumper wire connecting to the various pins as indicated here, right? Now this is showing how the Moto module is being connected to the power supply, and all denoted by usually the 12 volt plus minus 12 volt supply, the plus 5 volt supply, and of course the in and out. Take note that there's an earth wire here at the center here. This is usually connected to the 0 volt of the supplies. Now this is an overall connection which is shown. This is the diagram. This is the actual connection that is being made. Now, for section 3, we are trying to do the capture the steps response of the potentiometer. So naturally, the input is still the same, but the output we are measuring at the potentiometer. So using the VI, the front transfer function, we are going to run a 1000 millisecond, means in the X scale it will be 0 to 1000 millisecond, means there is 1 second of duration. And then of course we are going to pump in a unit step function, means that it's a 1 volt step function. The moment we click run, okay, so this is the front panel. Now the block diagram at the back basically looks this way, nothing unique and special. And of course, so if we were to track the input as analog signal to the V in and V out, and then measuring the potentiometer, okay, if we were to now, instead of using 1 volt unit step function, we're using a 5 volt step function here. And if you click run, you should be able to see a sawtooth waveform that is this way. Now this essentially actually is just a triangular waveform all the way up, but because the supply is limited to plus minus 5 volt, so therefore and when it hit 5 volt it would bend down, and then hit 5 volt it bend down again, etc. So if you look at this, there is actually 3 sawtooth, right? So each sawtooth is about 10 volt, 10 volt, 10 volt. So in total there will be 30 volts. So because of this fact that the output is a RAM, so it's a total magnitude multiplied by 1 over S squared. So therefore, essentially you will be having 30 over S squared over here. Of course, the U itself is a 5 volt step function, so it will be 5 over S. So G of S will basically be Y of S divided by the U of S, and you will be able to calculate and algebraically reduce it to get the final expression for your potentiometer. Now, for the tachometer wise, same thing. The connection is pretty much similar, except that you shift the connection from the potentiometer and then shift it to the tachometer point, right? Shift it between, swap between the two. And then again, now if we are using a 1 volt step function, we put 1 volt here. Again, the time maintained at 1 second. Once you click it, you will realize that it is actually looks like a first order equation. Now, for first order equation, we can model it slightly differently, meaning that we can use the generic equation for the first order. And then by doing so, if we are using the generic equation for the first order, we know that it is characterized by a few things, right? First of all, for first order equation, you basically need a K. So you got to determine what's the K value here. And then you need a tau here, which is 63%. What is the time taken to hit the tau? And then basically, if you know both of these, then you can write down the whole transfer function as K over tau S plus 1, right? So with that, that is the second method of how you can model a particular function, right? So in this lab, we show you basically 2 ways of modeling. So in summary, what lab 6 do is basically it links the block diagram manipulation, which is pretty complex subblocks, and then it try to simplify it into one single block by applying rule 1 to rule 8 in your beginning of chapter 4. And then also getting individual block transfer function via physical approach, which is not in lab 6, but modeling approach, which is what we discussed in lab 6. Okay, also using LabVIEW to inject unit step function and measure the output. So basically, we inject the unit step function, we measure the output. So here, potentiometer, you got a slope up, a ramp signal, and then of course, tachometer, you got a first order equation, right? And of course, for potentiometer, your input is 1 over S and output is whatever magnitude of your ramp function divided by S squared, because S 1 over S squared is actually a ramp function. So your model is gotten by output divided by input, then you will get your model. So that's the approach for the potentiometer. But for the tachometer, we are using first order transfer function, which is K over tau S plus 1. So essentially, you just extract the K value and the tau from the waveform, and you will be able to complete the modeling for tachometer, right? And with that, we basically ends the lab, and hope you will enjoy playing with the motor and characterizing the model. Thank you.